I'd like to welcome again everybody to this webinar. The topic of this webinar is the parametric optimization feature of VirtualLab, and I would like to demonstrate to you how the parametric optimization of VirtualLab can be used for the optimization of laser systems, including diffraction and interference effects. And I like to start with a short introduction to this problem of the optimization of laser systems. The parametric optimization feature of VirtualLab was released in version 4.10, so before Christmas, and it is available in the advanced version of the starter toolbox. Parametric optimization, or this new advanced version of the starter toolbox, enables the optimization of laser systems containing, for example, lenses, freeform surfaces, diffractive elements, hybrid elements or hybrid lenses, and also index modulated elements. So it is not only a tool to optimize lens systems, but these systems can contain much more different types of optical components. The parametric optimization is effective and useful if you have optical system with a small number of free parameters. I like to tell you later more about the optimization algorithms and for which number of free parameters it is efficient. But I like to mention that this is completely different from the diffractive optical element optimization that is included in the starter toolbox of VirtualLab, included in the diffractive optics toolbox of VirtualLab. In the diffractive optics toolbox, we have an optimization algorithm for diffractive element optimization that have several thousands or 10,000s of free parameters. So every pixel can be a free parameter. So in this case, we need another optimization algorithm that can handle this huge number of free parameters. Here the parametric optimization is made for a small number of free parameters, for example, to optimize an aspherical surface, to optimize the radius of a lens, or an grating that is just described by 3 or 4 different free parameters. In this case, the parametric optimization is a better choice. So we have here typically the following situations. If we optimize a laser system by a parametric optimization, we need to analyze the optical system several times during the optimization. Yeah, in several software programs, this light propagation through the laser system is often modeled by ray tracing, and this means if we do ray tracing, we neglect diffraction and interference effects, for example. VirtualLab has this powerful field tracing concept, and it allows to model the light propagation through the optical system, including diffraction, interference, aberration, and polarization effects. That means if we include this optical effects in the analysis of the optical system, we can also take into account these effects during the optimization. We can use diffraction and interference effects during optimization to reach a specific light distribution, or we can compensate diffraction interference effects if they are not useful in our application. So this is the major point if we compare parametric optimization of a laser system in VirtualLab with a parametric optimization, for example, in a ray tracing program, that we add to the simulation this diffraction interference effects. We can take into account these effects and yeah, have a better optimized laser system. Another important approach is if you do a ray tracing simulation of a laser system, you can analyze, for example, aberrations, or you can get a spot diagram, but you typically do not have merit functions that evaluate or that are actually required in your laser systems. The field tracing concepts of VirtualLab allows to optimize an optical system with respect to these method functions that are actually of interest in laser optics. For example, you can optimize beam parameters, beam diameter, m-square parameter, divergence angle. You can optimize an efficiency of a system, and signal-to-noise ratio, and uniformity error, or local contrast, and much more. So I will give you in the following an overview, an introduction to the parametric optimization. I will tell you which method function of VirtualLab can be used, how this parametric optimization concept works in general, and how you can specify the parameters in a parametric optimization document. After this introduction to the parametric optimization, I like to give you 3 different examples that are the optimization of a focusing system, the optimization of a fiber coupling system, and the optimization of a beam shaping system with a refractive cylindrical element that reshapes a Gaussian laser beam into a line. And at the end of the webinar, I like to show you that you can not only optimize predefined components and surfaces, but that also the optimization of user-defined or customized surface profiles is possible. So let's start with an introduction to the parametric optimization. I mentioned it already. Parametric optimization means that we have to analyze an optical system several times, and we need to calculate method functions during every analysis. And all method function results, so we can have different method function in an optimization, all method function results and also additional constraints are used to construct in common method functions. I will explain later how this works. And the parametric optimization is now varying the free parameter and just try out if there is an improvement of the common method function or not. And if there is an improvement of the common method function, it changes the free parameter in the correct way to get a step-by-step improvement of these method functions. We use in VirtualLab 2 different local optimization strategies for the free parameters, and this is that are the downhill simplex algorithm and Powell's direction search algorithm. So Powell's direction search algorithm is something like a gradient optimization algorithm, but it is doing a numerical calculation of the gradients. These 2 optimization algorithms are good for the optimization, let's say, of up to 23 parameters. Sure, it can be used also for 30 or 40 free parameters, so there's not a limit in VirtualLab. But the larger the number of free parameters, the more inefficient are the optimization algorithms. That means we just need more and more iterations to find the best solution. I like to tell you which method functions you can use in optimization. To optimize an optical system, you have to build up a light path diagram. You will see this later on an example. If you build up a light path diagram, you can use different detectors. And we have some detectors that return just a number, so we just evaluate the method functions that return one number. But we have other detectors that calculate, for example, in diagrams, or we have a virtual screen that show a field distribution. During the parametric optimization, it is just possible to use detectors that calculate a number for a method functions, because to construct in common method functions, we need different numbers that are combined to one method function. It is not helpful to have an output of a diagram, for example, or of a field distribution. So all detectors that do not return a number are ignored during the parametric optimization. In addition, you can define for every method function constraints. And for example, you can define an upper limit for the method function or a lower limit or a range so that the merit function value should be between two different values, and it is also possible to define a target value. Just to give you an example, let's assume you have a merit function that is the efficiency, the diffraction efficiency of a laser system containing, for example, a diffractive optical element. So, and your goal is to maximize this diffraction efficiency. And in this case, you would set as a constraint and target value and you would use a target value constraint, and you would set the target value, for example, to 100%. And this would mean VirtualLab tries to maximize this efficiency. I'd just like to mention, if you like to know more about this constraint definition for different merit functions, we have a technical note on our website. It's called TN021, and it can be downloaded from our webpage. So in addition to merit functions constraints, we have also structure constraints that limit, for example, the free parameters. So if you have a distance, for example, between two lenses, you can set, for example, a maximum or a minimum value, or again, a target value. We have also an additional type of constraints, and we call this in general structure constraints, and this is a little bit different from other softwares. Because for several applications, it is not sufficient just to limit or to have a constraint for the free parameter and direct constraint for the free parameters. There can be also more general structure constraints. And I like to tell you here the most important constraint that we introduced for VirtualLab. If you have, for example, surfaces with an aspherical or cylindrical shape, aspherical or cylindrical shape, it can happen if you use a lot of free parameters to model the surface profile that relative high frequency modulations of the surface appear. And this is probably not possible to fabricate this surface variations. And because of this, we introduced in general constraints that limits the local radius or that allows to limit the local radius of curvature of an aspherical or cylindrical interface. So you can again define for this local radius of curvature an upper or lower limit or a target value. So you can, for example, set the limit that an aspherical surface should have a local radius of curvature that is, for example, larger than 100 microns. And actually this limit depends on the radius of your tool that you use for the manufacturing of such a surface profile. Again, more information concerning these constraints of free parameters and of this general structure constraints can be found in this technical note 021. Yeah, from all merit function values and merit function constraints and from the structure constraints, and common merit function is returned. So every merit function constraint and every structure constraint return a number, and we need to combine all of these numbers on all of these results to a common merit function, and this combining is done by calculating a weighted sum of all constraint values. The weights that are used can be defined by the customer or by the user of VirtualLab, or can be set by VirtualLab. So let's come to the optimization of a system, and I like to switch to VirtualLab to give you an idea how it works. So let's assume that we have any optical system. This optical system must contain a light source and at least one detector that has a merit function that returns a number. For example, here just in virtual screen can be not optimized, but here I have, for example, a fiber coupling efficiency detector, and this returns a number. This is the fiber coupling efficiency, and it allows to this can be optimized during the parametric optimization. In addition, I like to mention the current parametric optimization is made for coherent monochromatic laser beams. So it's important that you use a light source that is switched in the monochromatic mode, that has just one wavelength, and that it is spatially coherent light. So if you have such a light path diagram, you have several options to start an optimization. In the toolbar, you find here in this region an button that allows you to generate a parametric optimization document. So this first page looks like this. Another option is you can click here on the system menu and select new parametric optimization. Or the same is possible here in the design menu. You can also select new parametric optimization. So, and I like to give you an introduction to this parametric optimization document before I will show examples. So I like to come back to the transparencies. So let's ignore the first page. It is just a drawing, but if you click on next, you will get a page like this, and it shows a list of all 3 parameters of your light path diagram. And you can select now from this list the 3 parameters that you like to use. For example, here I selected to use from one aspherical surface, radius, conical constant, and also 3 different aspherical coefficients. Okay, if you again click the next button, you see a list of all merit functions and detectors that are available in this light path diagram. Here, for example, just one detector and beam parameter detector was actually used, but if you have several detectors in your light path diagram, you see here a list. If you uncheck this detector, you can still choose to ignore this merit function during the optimization. And it is also possible, if you click on this edit button, to configure this detector. So this page is actually comparable to the parameter run of VirtualLab. Different to the parameter run of VirtualLab is now this following page. It is used to define the constraints for merit functions for 3 parameters, and also to define this additional structure constraints or general structure constraints. So you have 3 different sections in blue and red and then green section. The blue section shows all 3 parameters, and you can define for every 3 parameter a constraint type. You can see here, for example, here for this radius of curvature, an constraint range was defined. I like to show this here on the next transparencies. So this is here the section with the 3 parameters. We have here a section with the merit functions. You can define for every merit function a specific constraint, for example, a target value. And here this green section, this is for the definition of general constraints that are, for example, available for aspherical interfaces. Beside these 3 different sections, we have here also on the left lower corner a button that is called Optimization Tools. It contains some nice functions that are helpful for the optimization. I like to come back to this later. Now let's discuss here these different columns of this constraint specification page. We have here this column that is called use. It allows you to enable or disable one of these merit functions or one of these general structure constraints. So this is then an option to make a selection of constraints that should be used or, to construct these common merit functions. Okay, then we have a column that is called weight. Yeah, I think if you worked already with ray tracing software, you know what it means. You can just increase or decrease this weight for a specific constraint in order to make it more important or less important for the for this optimization. Then we have a column that is called constraint type, and here you can select between these different constraints that are available here. You can select range, that means you have a minimum upper and a lower limit, but you can also set just in lower or just in upper limit. And you can define, as you can see this here for the merit functions, and target value. And yeah, for example here, for that are our beam parameters for the radius in x direction, you can define a target value of 0. That means actually the VirtualLab would try to minimize beam diameter. So the values that are probably required for the constraints are defined in the following two columns. So we, for example, if we define a range, we have here the lower and the upper limit. But if you define if you have selected just target value as constraint type, you can enter here just one value. There's another section. This is actually the current value that is used in the beginning of the optimization. That means, especially for the free parameters, you see just the initial value. For example, here the radius of curvature is 2.75 millimeters. This is the initial value used for the optimization. And for the merit functions and also for these general structure constraints, you have just an NA. That means not a number. That just means that this value is actually not calculated currently. You can calculate these values here if you press this update button. So the calculation of the merit function is not done automatically because it can take time depending on your optical system. So a calculation of merit function can take several minutes. It's actually, from the calculation time, it's comparable to a normal analysis of a light path diagram. I like to mention that you are able to change this free parameter, the start values of the free parameters. So if you like to start, for example, with a different radius of curvature of your aspherical interface here, you can just double click here this start value of the radius and enter any other number that you like to use. And the last column contains the contribution of every constraint to the common merit function. So the contribution is a percentage value, and it gives just an it gives an impression how strong the influence of this constraint is to the common merit function. I mentioned it already. If you made here any changes, for example, of the weights or of the start values of the initial parameters, please press the update button to calculate here the merit function results and to calculate or update also the contribution to the common merit function. And at the end of this explanation of this page, I like to explain you what these optimization tools means that you have here. First of all, you have an option in this optimization tool. It is called reset to initial start values. That means VirtualLab always remembers the light path diagram that you used for the generation of the parametric optimization document. So if you made several changes and tries for the optimization, it can happen that it turns out that the optimization was going in the completely wrong direction. In this case, just press this button, reset start to initial values, and VirtualLab will set the start values of the free parameters back to your initial values of your initial light path diagram. There's also an option, it is called set optimized start values. It means if you did an optimization and it turns out this optimization was successful and you just like to, for example, activate additional free parameters or modify a little bit the merit function for a second optimization step, you can use this option, set optimize start values. In this case, VirtualLab will use the result of the previous optimization as a starting point for the next optimization. So if you don't press one of these two buttons here, if you don't use one of these two options, VirtualLab will always keep the start values as you define this on this constraint specification page. Okay, there are also some interesting settings here to control the weights. We have a function distribute contributions uniform. That means VirtualLab will automatically calculate all weights of the constraints so that every constraint has the same contribution to the common merit function. This makes especially sense for this merit function constraints. For example, if you, let's assume you have an efficiency, you have a uniformity error, maybe in signal to noise ratio, and you like to make sure that all of these constraints have a common influence on the or a uniform influence on the common merit function, just use this button and VirtualLab calculates the required weights. There's also one option that is called set contribution. In this case, you just enter a percentage value that is the contribution to the common merit function of a specific constraint, and VirtualLab is automatically calculating the required weight so that this constraint has the specific contribution to common merit function. And at the end, we have also two options, or two functions. One is a reset of the weights, so all weights are set back to 1. And reset all settings means VirtualLab will reset the weights, and it will also reset the start values to the values of your initial light path diagram. So after this constraint specification, we will have a page that allows the selection configuration of the optimization algorithm, so we can select between downhill simplings and this Powell's direction search method. We can select the maximum number of iterations, and we have an tolerance. That means if the change of the common merit function between two iterations is too small, VirtualLab will automatically stop this optimization. And here you can control the sensitivity of this algorithm. So for what is here the smallest change that is still allowed. And the last parameter is the initial step width scale factor. It means if VirtualLab starts to optimization, it has to vary the three parameters a little bit. And this the strength of this variation can be controlled by this scale factor. So if you decrease this scale factor, if you select a scale factor between 0 and 1, it means that VirtualLab will make smaller steps when it starts this optimization. And if you set a scale factor larger than 1, it means VirtualLab will do larger steps, so it will also search a little bit larger area around this initial start values if it starts this optimization. The last page is now used for starting and evaluation of the parametric optimization. So you have the start button to start the optimization, and if it is running, it is changed in the stop button, and you can again stop this optimization. You see all three parameters and merit function values, and you will see also the value here of this common merit function. This is here the first row. You can mark a row in this table and click, for example, output from selection to get a diagram showing the change of a free parameter or a merit function depending on the number of iteration. So at the end you have here in the right lower corner another button. It is called Show a Light Path Diagram or Show LPD, and it has two different options. It can return you your initial light path diagram that you used for the generation of the parametric optimization document, and it can display you a light path diagram containing the optimized parameters. So I think this was now a lot of theory and maybe a lot of information. I like to show you now 3 different examples, and I think this makes it a little bit more easy to understand how this optimization works. And I like to start to show you the parametric optimization of a lens system for focusing of a laser beam. So we have here the following setup. We have a collimated laser beam with 532 nanometer wavelengths. The width is 2 millimeters. And this collimated laser beam illuminates a doublet lens. This doublet lens consists of 2 spherical lenses. Every spherical lens has 2 spherical surfaces, and the lenses has different or made of different glasses. So we have 4 spherical surfaces, and these 4 spherical surfaces are in VirtualLab modeled by the conical interface. The doublet lens has a diameter of 10 millimeters, and the goal is to focus the light in a distance of 20 millimeters. So it's now just 1 moment. I will stop here because we have 1 question. And the question is, will the optimization of multiple wavelength systems be available in future releases of VirtualLab? And the answer is yes, it will be possible. But actually, the optimization algorithm would work also for multiple wavelengths, but the current problem or limitation is that you do not have merit functions that can be used for multiple wavelengths. The same is actually for spatially partially coherent light. This is the reason that we currently restrict to monochromatic coherent light, because we need some merit functions that will return or will calculate just a number and describe the quality of polychromatic or partially, in general, partially coherent light. And as soon as we added for different situations good merit functions, it will be able or will be possible to use it during the optimization. But for several applications, this requires still some research, and this is the reason that these merit functions are currently not available. So if you have any application or any ideas what you like to do, or which polychromatic system you like to define, it is always nice if you would give us some feedback and describe the merit functions that you like to use, and then we have a good idea what we need to implement. So any other question? Okay, then let's come back to this example. So this was the optimization of a focusing system. I mentioned we have a doublet lens, and this doublet lens should have a back focal length of 20 millimeters, and the goal is just to generate a very narrow and perfect laser beam in the target plane, in this focal plane. So in the doublet lens, we use 2 different glasses, BK7 and SF6 from the SHOT catalog. We have a diameter of 10 millimeter. The distances, the center thickness of the lenses is set to 3 millimeters, and the distance between the lenses is set to 0.5 millimeters. And I assume for this optimization that these distances are fixed. I set an initial radius of curvature of the spherical surface of plus minus 25 millimeters, and this is actually what I like to optimize. So let's discuss what is the goal of the optimization. Again, the goal is to optimize the conical interfaces, especially the radii of this 4 conical interface in such that the focus of the laser beam in the focal plane is smallest or is minimized and has a very good quality. So the three parameters for the optimization are the radii of these four conical interfaces, and the target function or the merit function that we will use are the beam parameters and especially the beam radius in this back focal plane. It would be, I'd just like to mention, it would be possible also to use the m-square parameter in addition to the beam radius, but our experience is just if you minimize the beam radius, it automatically means then that the m-square value should be or must be close to 1, because otherwise you will not get a narrow beam in the target plane. So now I like to switch from the transparency back to VirtualLab. So this application scenario has number 101. I like to mention that this application scenario is also available on our web page. So this is the initial light path diagram that I will use for the optimization. So we have here the collimated laser beam with 2 millimeter radius and an wavelength of 532 nanometers. For the simulation of the doublet lens, I use an optical interface sequence component. So we have here 4 conical interfaces. And this is just here a component that marks here the back focal plane in 20 millimeter distance. I will use the automatic propagation operator to propagate in free space from the lens to the back focal plane, because depending on the parameters of this radio of curvature, different propagation techniques can be helpful. In the target plane, I have a virtual screen and a beam parameter detector, but I like to mention again, just the values of the beam parameter detector can be optimized. The virtual screen is just for visualization of the optimization result. So now it is easily possible to construct a parametric optimization document by clicking here, for example, this button here, new parametric optimization document. But actually in this example it is already prepared, and I will just load this optimization document and show you the settings. So on the first page, as I mentioned in my previous introduction, we have a list of all 3 parameters. So we see here the 3 parameters of the Gaussian light source. That are the 3 parameters of the optical interface sequence component, number 1. And here we have the free space in front of this identity operator that is used to mark the target plane and the distance to the screen in the beam parameter detector. I selected here for the optical interface sequence component the radius of curvature of every conical interface as a free parameter. On the next page, I see the detectors that can be used for the optimization. That is here just the beam parameter detector. And if I click here on open, I can select which beam parameters should be calculated. So every beam parameter is one merit function that is used for the optimization. And I selected here just in beam radius in X and Y direction. I'd just like to mention, actually the beam radius in X or Y direction would be sufficient, since this is a rotational symmetric system and we have a rotational symmetric laser beam. If you like, you can in addition select other beam parameters, for example the m-square parameter. Now let's come to the constraint specification page. It is actually quite easy. Here in this blue area we see all 3 parameters, so that are these 4 radii of curvature. And this red area, this is here the beam parameter merit function, that are the radius in X and Y direction. I select here the following constraints. The radius of curvature of every conical interface is limited typically in a range from -to minus 10 kilometers to 10 kilometers, so it is nearly free, so we can also use a nearly plane interface if this should be a best solution. In this column you see the start values that are just plus minus 25 millimeters. And here in the red section you can see the constraint for the radius of curvature, and I selected here a target value constraint and defined in value of 0. That means VirtualLab will try to minimize the radius of in x and y direction, the beam radius in x, y direction, so that it comes as close as possible to 0. Sure, it will be not possible to have a beam diameter of 0, but we have a lot of pressure for the algorithm to minimize the radius of curvature. So if I click now the update button, VirtualLab will calculate the current beam parameter values and the contribution to the common merit function. And you see already that this takes a little bit time, and this is the reason that we do not do this update automatically. Okay, now you see here we have a current value of 2 microns. The reason is that this is actually optimized here, nearly optimized, and you see here the contribution to the common merit function. You can change now here the weight, for example, to, and press again the update button to change here the contribution to the common merit function. This makes just sense if you have a non-rotational symmetric system, or if you have a laser beam that is not rotational symmetric. So on the next page, I selected here the downhill simplex algorithm for the optimization with a maximum number of 500 iterations and an tolerance of 1 to the power of minus 12. So this would mean that this is actually a relatively long calculation with a lot of iterations because of this high accuracy. And the initial step with scale factor is 1. So you could start now the optimization if you click here this start button, but here in this stored optimization document, this optimization is already finished, and because depending on your optical system, the optimization can take a long time. It is much more time consuming than the optimization by ray tracing, because already one analysis of the optical system takes more time than a ray tracing analysis, and so an optimization can run maybe a half hour or also several hours depending on your optical system that you need to analyze. So to see the result, for example, to see the convergence of the optimization, you can mark here this row, for example, for the radius in x direction, and you could double click here on this row to get a diagram, or you can also just mark it and click output from selection. And then you get a diagram like this, and you see here in the beginning the radius is quite large, yeah. And but step by step it is reduced. Yeah, you see that especially in the beginning there are some strong variation of the radius because VirtualLab is testing this region around the initial values, but later it converges relatively fast to a good value. So the optimization needs here around 220 iteration. I like to mention again, compared to a ray tracing optimization of such a lens system, the difference is here that we have a beam merit function that takes into account really the beam size and shape, and this is actually more a natural merit function for laser optics. And in this optimization also diffraction and interference effects, but also the lens aberrations are included. So and at the end we get the following light path diagram. We can display this if you click here on show optimized LPD. And so, and if you click here on the go button, you see here the output in the target plane of the optimized system. Takes again a little bit time to analyze this. So I will switch to a false color distribution, and now you see here the Gaussian beam in the target plane. So it is nearly perfect. I just like to show you that actually also the m-square value is quite good. So actually I did not use the m-square value as a free parameter for the optimization, just the ratios, but I just like to show you that also the beam quality is very good. And so I activate from second analysis the m-square value, and we'll see here the result in this detector result window. Okay, and now you can see here that the m-square value is 0.06, so this is nearly perfect. Yeah, this was an example that demonstrates the optimization of a focusing system with a doublet lens. Sure, instead of a doublet lens, you could use here also an aspherical lens. This would be no problem. I just like to summarize this. This example demonstrates the application of the parametric optimization for the parametric optimization document for the optimization of a laser system. The optimization takes into account diffraction, interference effects, aberrations, and if required also polarization. And sure, you can define also merit function that need access to amplitude phase, to polarization. That are typically this merit function that are really of interest for your laser system or for your application. I just like to mention that you can use sure also more free parameters, not only the radius of curvature of the lenses. You could optimize also the distance between the interfaces. Or for example, you could optimize the parameters of your light source. So in case that you do not have questions, I would like to come to the next example. It is actually related to the previous example because I like to show you now the parametric optimization of a lens system for fiber coupling. So the goal is to couple the light of a single mode fiber in the light of a single mode laser into a single mode fiber, and the goal is to maximize the fiber coupling efficiency. So that means I will assume again a collimated laser beam, in this case with a wavelength of 632 nanometers and a diameter of 4 millimeters. And the goal is to focus this laser beam by an aspherical lens with a radius with a diameter, an aperture diameter of 8 millimeters, and in difference to the previous example, it is now important that the laser beam in the target plane has not only a quite good shape, but that it has also the correct size, so that you get an high coupling efficiency. That means we have here approximately a distance of 16 millimeters of the fiber from the second surface of this aspherical lens, but this distance must be also changed a little bit during the optimization so that the NA of the lens fits exactly to the fiber NA, and the fiber NA is here 0.12. I like to give some comments concerning this aspherical lens. As an initial system, we assume that this aspherical lens has a radius of curvature of 8 millimeters and a conical constant of 0. In addition, I assume that both sides or both surfaces of this aspherical lens are coated with magnesium fluoride just to reduce the Fresnel losses, because otherwise you would lose around 8% of the energy just because of Fresnel reflection. So the goal of the optimization is now the following. We need to optimize radius of curvature, conical constant, and here's a mistake in the transparency. So we need to optimize radius and conical constant of this aspherical interface, and we need to also to optimize the distance here between lens and fiber, such that the fiber coupling efficiency is maximized. So we like to get an efficiency close to 100%. And I will not use for the optimization aspherical coefficients. I will just restrict on radius and conical constant. So three parameters are radius, conical constant, and distance between lens and fiber. And the target function or the merit function to be optimized is the fiber coupling efficiency. So I will jump again to VirtualLab to show you this optimization here of this example. Let's start with the initial system. We have again a Gaussian laser beam here with 2 mm radius, that means 4 mm diameter. Wavelength of 632 nanometers. For the modeling of this aspherical lens, I am using again the optical interface sequence, but I have now just a conical interface and a plane interface. So a conical interface is just allows just to model simple aspheres with that are described by a radius of curvature and a conical constant. Sure, for more general aspheres, also the aspherical interface of VirtualLab can be used. I will use it in the following example. But here let's restrict to the conical interface. The initial distance between lens and target plane is 16 millimeters. I like to mention, as you know this also from ray tracing optimization, it is since we use here local optimization, it is important to have also some good initial guesses of the three parameters. So if I would set, for example, here the distance to, let's say, 100 millimeters, it would be really difficult to find here this best solution for the fiber coupling. So it is helpful to make a rough estimation of the distance that follows just from the fiber NA, and to use this as an initial guess for the optimization. Merit functions here are, or is just the fiber coupling efficiency. This virtual screen is just used to display the light distribution in the target plane. And if I analyze this system, I get a light distribution like this, looks Gaussian, but the size is completely wrong, and the fiber coupling efficiency is 0.03%. So now it's again possible to generate an optimization document. So I will load here already this prepared document. You see here again a list of all three parameters, and I selected here for the optical interface sequence component and the conical interface, the radius of curvature and conical constant as three parameters. In addition, also the distance between here this coupling plane and the lens. So this in-coupling plane, this is modeled by an identity operator, so it is doing nothing. It is just a mark of this plane. And here this distance here, this position of this identity operator is marked as three parameter. The fiber coupling detector is the only detector that can be used for the optimization, and it's again possible to configure it. I selected here a fiber NA of 0.15, assuming a perfect single mode fiber. That means I assume that the fiber mode is also a Gaussian beam. If it is not, you can also set a specific signal field, this or a specific fiber mode. This is the constraint specification page. It shows here the three parameters. This is the blue section. We have radius of curvature, conical constant, and the distance between lens and target plane. And I have a range constraint, but actually the range is so huge that the algorithm has a big degree of freedom to modify these three parameters. Start values for the radius of curvature is 8 millimeters, conical constant is 0, and the distance between fiber and lens is 16 millimeter. And here, this red line, this is the fiber coupling efficiency, this is the merit function that we will use, and the constraint is here just a target value constraint of 100%. So the goal is to have an efficiency and coupling efficiency close to 100%. Can again press update to see an update of the merit functions, and yeah. Let's come to the general settings page of the optimization algorithm. I will use again the downhill simplings algorithm, 500 iterations, but now the tolerance is just set to 1 to the power of -5. This is actually sufficient because we don't need an accuracy of the, or an optimization of the fiber coupling efficiency for, let's say, 5 or 10 digits after the decimal point. Yeah, so 1 to the power of -5 is already 10 to the power of -5 is already very accurate. Initial step width scale factor of 1 is okay. That means if you have a factor of 1, the search is not too local, so VirtualLab is searching a little bit larger area, but it is a good compromise between a local and an global optimization. If you would set here a larger factor, the downhill simple algorithm would search a larger area for a good solution. Again, the optimization was done before. It takes here maybe around, let's say, 20 or 30 minutes to optimize this. I like to show you again this progress of the optimization here, for example, in diagram showing fiber coupling efficiency. You see that there's in between always a strong variation. This is not a smooth convergence to the target value, because this downhill simplings algorithm always tries some parameter combinations that could give probably a better result, yeah, but not always a real improvement is reached. It can also happen that a selected parameter combination gives just a decreasing of the efficiency. So this is a typical effect of the downhill simplings algorithm, that it continuously tries to tries different parameter combinations, and some lead to strong improvements and other not. But this advantage has also, or this behavior has also the advantage that the downhill simplex sometimes finds maybe a minimum of the merit function beside any other local minimum, and so that it not fast starts within a small minimum of the common merit function. You can mark here also other rows, for example here the change of the radius of curvature of the Koenig interface. You can see here how it converges to the target value, and this here shows the convergence of the common merit function. Again, it is possible to show or display the optimized light path diagram, and let's analyze this. And so this is the intensity distribution. It's again a nice Gaussian beam, and the fiber coupling efficiency is here 97.4%. This difference to 100% can be explained because of the Fresnel losses. So the magnesium fluoride is not in perfect coating. It reduces the Fresnel losses, but the Fresnel losses are not zero. So if we would reduce, disable the simulation of Fresnel losses, we would have nearly 100% of coupling efficiency. I just like to show this. If you click here, so I open the dialog of the optical interface sequence component. If you click on propagation, geometrical optics, edit, then we can switch here from a simulation of refraction with Fresnel losses to a simulation just of refraction simulation without Fresnel losses. That means the Fresnel losses are ignored. And if I repeat this analysis, we will get an efficiency close to 100%. This is what you see here. The right lower corner, we have now 99.9%. So that means this is actually the best solution. So we have now one question that I like to answer. And the question is, so in which cases should we use the downhill simplex algorithm, in which cases we should use the Powell direction search algorithm? This is actually not easy to answer, because so my experience is that we have a little bit different behavior during the optimization, especially concerning the sensitivity to local minimas and maximas of the merit function. First of all, I like to say, in difference to, for example, in a ray tracing optimization, we have often merit functions that have a huge number of local minimas and maximas. This comes just from the more complicated nature of the merit function, but also from it comes also from diffraction and interference effects. It can happens very fast that you get some different, for example, rings, interference rings, that lead to a variation or to several maximas and minimas of the merit functions. In addition, we have always in every optimization or analysis a limited numerical accuracy, and this accuracy change if we modify the free parameters. And it means we get always also a little bit noise over the merit function that comes just from the change of the numerical accuracy. This is really difficult to handle these noises or this huge number of local minimas and maximas, so that the optimization do not stagnate suddenly. My experience is that especially the downhill simplex algorithm is not so sensitive for stagnation, so it can, especially if you have a small number of free parameters, for example below 10 parameters or so, it can find a good solution quite fast without stacking on local minimas. The Powell direction search algorithm often needs more time. If you have a lot of comparable local minimas and maximas, it sometimes also hangs faster on a local minimum without continuing the search. This is just my experience for several laser systems. But at the end, I always recommend to try out also both algorithms, because we can just find different solutions, and it is in general not clear what is always the best solution. This is also the reason that we offer two algorithms, because we cannot give a general suggestion for all laser systems which algorithm is better. For these examples that I show here, I make a suggestion of the algorithm, but you can be sure that I tried both algorithms and just to find out what is the fastest and which algorithm finds the best solution. Okay, any other question? Okay, now I like to come to the last example. So we are already here a little bit delayed, and I'd just like to show you here the last example. It's actually also the most complicated one. This is the optimization of the parametric optimization of a refractive beam shaping element for the shaping of a laser line. It means I will use a refractive cylindrical aspherical lens like element that introduces in one direction phase aberration to reshape a Gaussian laser beam into a laser line with a top hat shape. So this is we have the following system to be optimized here. This is the initial collimated laser beam. We have a cylindrical lens-like element with an aspherical cylindrical surface. So we have just a modulation in one direction along the x-axis, and the goal is to reshape this Gaussian laser beam in a target plane in a distance of 100 millimeter in such a top hat. So this is actually a really difficult optimization, since we can get several diffraction effects if we introduce the wrong aberrations, and it is also an example that shows that the optimization or the optimization strategy is important to find here a good solution. So the optimization task is here now the following. The goal is to optimize a cylindrical interface such that the signal-to-noise ratio and the efficiency are maximized. So that means our three parameters here are the radius of curvature, conical constant, and the aspherical coefficients 1 to 5 of the cylindrical interface. The method function that I will use to evaluate the quality of this generated light distribution are the signal-to-noise ratio, SNR, and the conversion efficiency. And I like to tell you a little bit more concerning this method function. These method functions are included in the diffractive optics method function detector, and both method functions, SNR and conversion efficiency, require the definition of a signal or reference field. The signal field, this is what you see here on the left, in the left image. This is actually, let's say, the perfect intensity distribution of your line. In addition, you need to define a signal region, and the signal region, this is a mask, and it marks in the area in that the method functions will be evaluated. Outside of this, it means inside of this area, SNR and efficiency are optimized. Outside of this area, there can be any light distribution, for example, stray light. So this is something what you cannot do if you optimize such a beam shaping element by ray tracing, because in ray tracing you don't have stray light or you have not a measure for it. But in VirtualLab it is possible, because we include diffraction and interference effects, and this means automatically that you can use here also some stray light, or that you can scatter light to higher angles by introducing high frequency modulations of this cylindrical interface, and so to increase the quality of your laser line. I like to mention that you can do the optimization of such a line beam shaper also by any ray tracing software. The difference is, in ray tracing you ignore diffraction and interference effects, so it can happen that you optimize a system, but you cannot take into account the diffraction effects, you just see it after fabrication. And the second point is, if you use geometrical optics for the optimization, you cannot use diffraction interference. It means if you work at the resolution limit of your optical system, you can probably not completely resolve here, for example, the edges of your line or other details as you like to have this. In VirtualLab, we can use diffraction interference to increase the resolution and to come really close to the optical resolution limit. So the parametric optimization is done in this example in a two-step process. In the first step, I will optimize just radius and conical constant of the cylindrical interface. In a second step, I will optimize, in addition to radius and conical constant, also the 5 aspherical coefficients. So this two-step process helps the algorithms to find a good solution. If I would activate all three parameters at once, I would need a good initial guess of the 3 parameters to find here the best solution. But if I do this in a two-step process, I limit a little bit the degrees of freedom, especially in the first optimization step, and so I will come closer to a good solution. Okay, I will switch again to VirtualLab. Let's start here with the initial system for the optimization. We have here again a laser system. I will use in the following just a one-dimensional calculation, since this cylindrical lens-like element just acts in one dimension, in along one axis. It makes no sense to make a two-dimensional simulation. A one-dimensional simulation is faster and is sufficient good for the optimization. The beam shaper is modeled by an optical interface sequence component with a cylindrical and a plane interface. And the start values are an radius of curvature of 15 millimeters. Conical constant and aspherical parameters are 0. So here in the target plane, I use a diffractive optics merit function detector. I selected here conversion efficiency and signal to noise ratio, and a signal field and a signal region are set as mentioned on the transparency. So this is the signal field, this is the signal region. So the current quality is quite bad. So if we see here, the light distribution in the target plane is just in Gaussian, and the efficiency is around 70%. This is not so bad, but the signal to noise ratio is around 6 decibel. So, and good quality of a laser line would mean to reach a signal to noise ratio larger than 40 decibel. So let's come to the first optimization step. That means just the optimization of radius of curvature and conical constant. So I selected in this first step here just the radius of curvature and the conical constant as an free parameter. On the next page, the diffractive optics merit function detector is selected. And here we see on the constraint specification page the constraints for free parameters and merit function. The blue section that are the free parameter constraints, I actually keep this nearly free. For the diffractive optics merit function detector, I set for the signal to noise ratio and target value of 60 dB. This would be actually very good. And the conversion efficiency is set to as a target value of 100%. So actually in the initial values here, the initial values for the initial values actually in weight of 1 would be entered here if you, or would be selected if you create this optimization document and if you download it from the hard disk. And if you now update the merit function, you would see here that you have actually not the correct weights. You see, for example, the efficiency here is 70%, but the contribution to the common merit function is too small. I think we need a larger weight for the common merit for the conversion efficiency, so that it has also an influence on the common merit function. Otherwise, just the SNR would be optimized on the cost of efficiency. And now we can use now in the optimization tool this function distribute contributions uniformly. In this case, VirtualLab automatically calculates here the weight of the, recalculates the weight of the conversion efficiency, so that it has also 50% influence or contribution to the common merit function. Okay, there are two questions. Just one moment. I like to finish here the explanation of this page, and then I will come to the questions. Okay, and here this green line, that is here such a general constraint of the cylindrical interface. In this case, you can limit the minimum local radius of curvature. You can set this, for example, to let's say 100 microns. That means if you use, for example, a CNC machine to fabricate such a cylindrical lens, and your tool has a radius of 100 micron, you should enter here this tool radius also as minimum local radius of curvature to make sure that you can fabricate this lens. And here you see the current local radius of curvature rate is 50 millimeters, since this is currently still spherical. Okay, now let's come to the questions. Okay, one question is, okay, is it possible to optimize or to use lenses from a lens catalog during the optimization? So, and the answer is no, this is not possible because we have currently no lens catalog. So as soon as we will have a lens catalog, we will also find a solution to use these lenses in the optimization. But currently this is not possible. So the second question is there an upper limit of the number of surfaces that can be defined in the optical interface sequence? And there's no limit. So you can in general define so much surfaces or so much components as you like in a light path diagram. But sure, if you have more components in a light path diagram, if you have more surfaces, the simulation is typically more time consuming, and sure also the optimization will take more time. Okay, are there any other questions? So otherwise, let's come back here to this optimization. So this was here the constraint specification, and I used again the downhill simplings. 500 iteration is sufficient, and I set the tolerance to 10 to the power of -5. And now we can run here the optimization. This is now actually quite faster. Let's see if we can do this here nearly live. Okay, since this is just a one-dimensional simulation, it is running relatively fast. If the simulation is still running, you can still show here, for example, the convergence here, for example, of the SNR, just to show if VirtualLab is already close to a solution or if it is still searching around for a good parameter combination. Here you can see, for example, already after 25 iterations that we are already close to an SNR of 15 dB, but it is still improved, and it means VirtualLab did not find actually the best solution. It is still needs more time. If VirtualLab is coming close to a perfect solution, you can see this that actually the values of the merit functions do not change very much. Okay, this is, for example, what you see here, relative strong changes in the beginning, but now we have nearly in convergence, and this here is just the current value that is under progress. So I think it's now finished, yeah, after 76 iterations, and we found here an SNR of 21 dB. This is much better than before, but it is not the best. The efficiency is around 92%, and I like to mention that I did not edit encoding to the beam shaver, so that are mainly the Fresnel losses. So I like to show you the optimized system and analyze it. So, and this is actually the shape of the optimized line. It looks a little bit like the line, but you have a lot of rings here, interference rings, and this is normal because we have not enough degrees of freedom. We have used just a radius of curvature and a conical constant, and we cannot expect a perfect top hat line. So we need more degrees of freedom, and this can be done by a second optimization step. I will load again here this optimization document. And in this optimization document, I enabled, in addition to the radius of curvature and the conical constant, also the aspherical parameters and the aspherical coefficients 1 to 5. And all other settings are actually comparable. The only difference is if I'm updating here, let's update here the merit function contributions, that I changed a little bit the weight of the conversion efficiency. I increased the contribution of the SNR to the common merit function to around 80%, because the efficiency, the current efficiency is already not bad. With 95% efficiency, we have actually just Fresnel losses. But we need to improve the SNR to get a real line. And because of this, I change the weight of the conversion efficiency so that the contribution of the SNR to the common merit function is larger. I use again the downhill simplex with 5,000 iterations. The tolerance is set to 10 to the power of minus 4. And I set now an initial step width scale factor also of 10 to the power of minus 4. So I reduced very strong this initial steps with scale factor because we have already a relative good solution. Actually, it is not required to change the radius and the conic constant too much. We just need aspherical coefficients to improve the result, and the aspherical coefficient values are typically relative small. Because of this, I set here this small initial step width scale factor. I cannot show the optimization here live because we need here around 800 iterations. This takes a little bit time. But just to show you the conversion, this is here the result. This is the SNR depending on the iterations. And you see that VirtualLab here found also two local minimas, but it turns out that this is not the best solution, and so it continues the optimization, and at the end it reaches, VirtualLab reaches an SNR of 44 dB, and this is already quite good, especially if you take into account that we use here a simulation in float precision, so just with 7 decades. 44 dB means that the average difference between the noises and the desired intensity distribution is smaller than 0.1%. And again, I like to show you the optimized light path diagram and analyze this. And now it looks like this. So this is the squared amplitude or intensity. You still here see on the top some ripples. So it would be possible to make a future optimization, but I think in this case we need more aspherical coefficients. But actually, if you know how sensitive these beam shaping elements are for fabrication tolerances and for deviations of the incident laser beam, actually it makes no sense to make a future optimization because typically the tolerances or the effect of the tolerances will be much stronger than here this remaining intensity variations. So just to summarize this, we have here an efficiency in the first optimization step just with radius of curvature and conic constant. We have an efficiency of 92% and an SNR of 21 dB. In the second optimization step, in that we use in addition the aspherical coefficients, we could increase the SNR to 44 dB, what is already a very good solution. So this example shows you that VirtualLab can optimize also a refractive beam shaping system. The simulation can take into account diffraction, interference effects and aberrations, and you can use merit functions as, for example, SNR or conversion efficiency for the evaluation of the quality of this line. And I'd like to mention also the uniformity error could be used for the optimization. I like to mention that this optimization is already relatively complicated. You need a two-step process and also several iterations. And the reason is that we do not have any clever initial guess of the three parameters. We are working currently on a session editor that will simplify this work for you. And it is planned to release it in early summer this year. And it will use an analytical geometrical optics approach to calculate an initial guess of the surface profile of such a cylindrical or aspherical or freeform surface. And in this case, the parametric optimization is just used to make an improvement of this initial guess to reach a little bit higher efficiency and SNR, but typically this will reduce dramatically the calculation time and the number of iterations that are required. And so we will show this in another seminar as soon as it is available. So at the end, I'd just like to mention that the parametric optimization is not limited to conical or aspherical or cylindrical surfaces. In general, it can be used for any customized freeform surface. And one way to customize a surface profile is the programmable interface. The programmable interface allows you to enter a small equation, we call this a snippet, for the modeling of a surface profile that is not included in VirtualLab. And if you define such a snippet, you can define global parameters, and these global parameters can be found here in this table. And these global parameters can be varied, for example, by the parameter run of VirtualLab. This is good for tolerance investigation, or we can be optimized by the parametric optimization document. And I just like to show this here on one simple example. This is an anamorphic surface. Actually, this snippet for the anamorphic surface is available at our web page or in our download area of the web page. So you can also use it for your system simulations. Here I have a component, an optical interface sequence component consists of a plane and a programmable interface, and the programmable interface contains this anamorphic surface snippet. This anamorphic surface has in this case here a shape like this. And so it would be possible to optimize the parameters that you see here in this table of the programmable interface here. I like to show this. If I open here an parametric optimization document, you see again a long list of 3 parameters, and here that are the 3 parameters of the programmable interface, and here you see, for example, the conical constant in x and y direction, and also the radius of curvature in x in y direction. So that are these 3 parameters that you can that are just defined by this snippet. So this makes VirtualLab very flexible. It makes also gives you a high flexibility to define freeform, refractive, diffractive, and hybrid surface profiles, and to do a parametric optimization of the 3 parameters of these surfaces. So this is already the end of the seminar. I like to give you a short summary. I showed you that VirtualLab is able to do a parametric optimization of laser systems, including diffraction, interferences, aberrations, and polarizations. These laser systems don't need to contain lenses. It is also possible to optimize diffractive or in general diffractive, refractive, and hybrid freeform surface profiles. And we have also special merit functions, as for example the diffractive optic merit functions that can be used to optimize customized light distribution, to optimize elements that generate customized light distribution. The advantage of the field tracing concept that we use for the analysis of optical system is that you can optimize optical system with respect to merit functions that are actually of interest in laser optics. So you don't optimize spot diagrams, you optimize efficiencies, signal to noise ratios, contrast, or uniformity errors. I showed you the optimization of focusing systems, fiber coupling systems, and refractive beam shading systems, but sure, much more is possible. And at the end, I just give you a brief overview that you can define customized freeform surfaces, for example, by the programmable interface. You can define global parameters, and these parameters can be optimized easily by the parametric optimization. And this gives you the big advantage to optimize also complicated freeform, diffractive, refractive, and hybrid surfaces that you need for your application. So thank you very much for your attention. And yeah, if you like, you can ask now some questions that you might have. I'd just like to mention, if you like to get the transparencies or the video of this presentation of this webinar, just send an email to hagen.schweitzer@lighttrans.de or .com. Both email addresses will work, and we will send you the transparencies and the video. So, but in addition, you can now ask some questions.